On March 14, 1949, Einstein opened a birthday gift and fell silent. Not the polite hush of someone feigning gratitude for a poor present, but the silence of a man staring at something he could not refute and desperately wished he could. His closest friend, Gödel, had just placed in his hands a mathematical proof built from Einstein's own equations, demonstrating that in the right kind of universe, time simply does not exist. No flaw, no slip, no error in the working, only a conclusion nobody wanted to be true. Physics filed it away and carried on. Yet the evidence has been quietly accumulating ever since, and laboratories today are now measuring the first direct signs that Gödel was right. If you are new here, welcome to Sundown Science. Hit like, subscribe, and settle in, because tonight I am going to walk you through one of the most quietly unsettling discoveries in the history of physics. A proof that the universe may be fundamentally timeless, and why the most precise clock ever built seems to agree. Get comfortable, and let's ease into this one slowly. Part 1. The birthday problem that breaks intuition. Snow had been drifting over Princeton for most of March 14, 1949, and the streets carried that particular hush only a university town can manage on a cold midweek afternoon. Albert Einstein was turning 70. His colleagues had arranged a small gathering at the Institute for Advanced Study, and by most accounts it was a warm occasion, full of the awkward reverence people show to a living legend who still arrives at his desk every morning. There were speeches, there were flowers, and then there was Gödel, appearing at the door of Einstein's home with a handwritten mathematical proof tucked under his arm like a folded newspaper. This was not a sentimental gift. Gödel was not a sentimental man. He was small, precise, and deeply anxious, and he happened to be the most consequential logician since Aristotle, someone who had, back in 1931, detonated a bomb at the center of mathematics itself with his incompleteness theorems. He had proved, using mathematics, that mathematics contains truths it can never prove. The scientific world had spent the better part of 2 decades absorbing the implications. And now here he was, handing Einstein a birthday present that, at its core, was a proof that the universe Einstein had described contained something Einstein clearly did not want it to contain. The proof was not abstract speculation. That is the first thing to grasp before anything else can be understood. Gödel had not invented new physics. He had not modified Einstein's equations, added exotic terms, or smuggled in assumptions from philosophy or metaphysics. He had taken Einstein's own field equations, the equations of general relativity, the equations that describe how matter curves space and how curved space tells matter how to move, and he had found a new solution to them, a valid, mathematically consistent, formally correct solution. The solution described a universe that rotates, not a universe in which galaxies spin or planets orbit, but a universe where space-time itself, the entire fabric of reality, turns as a whole. And Gödel had shown that in such a universe, the geometry of space-time becomes so severely warped by that rotation that something extraordinary follows as a pure logical consequence. You can draw a path through that universe, a path that always moves forward in time by every local measurement, never exceeds the speed of light, and obeys every rule of physics at every single step. And that path curves back on itself. It returns to its own starting point, not to a similar place at a different time, but to the exact same point in space-time, the same moment, the same place, the same event. Physicists call these structures closed time-like curves. The name sounds technical, but the idea is almost unbearably simple. Imagine leaving your house at noon and walking forward, never doubling back, always moving in what feels to you like the future. And yet, after a long enough journey through the right kind of space-time geometry, you arrive back at your own doorstep at noon, the same noon before you left. and the rules of physics, as Einstein wrote them, apparently have nothing to say against it. Time in Gödel's solution does not point in one direction the way a river points to the sea. It curves. It closes. The distinction between before and after, between cause and effect, between the past being gone and the future being unwritten, all of that collapses in the Gödelian universe like a house of cards in a light breeze. And here is what makes this more than an interesting mathematical footnote. The house of cards it collapses is not just our intuition, it is our entire framework for thinking about how anything happens at all. If a closed, time-like curve exists, then what does it mean for an event to have a cause? If you can in principle trace a path back to the moment before a cause occurred, then was it really a cause? If the past is not sealed and finished, if it is in principle reachable from the future, then the very concept of explanation, of one thing leading to another, of the universe unfolding in a sequence, all of it becomes deeply questionable. Gödel was not merely pointing to a curiosity, he was handing Einstein a proof that the logical structure of time itself might be an illusion. And he had built that proof entirely out of Einstein's own materials. Einstein looked at the mathematics, and this is where the story begins to show its true texture, because Einstein did not dismiss it. He could not. The equations checked out. Part 2, Einstein's silent reaction. There is a particular kind of intellectual discomfort that scientists rarely discuss in public. The discomfort of confronting a result that is formally correct and yet feels fundamentally wrong in a way you cannot quite articulate. Einstein knew this feeling. He had spent the last 2 decades of his life fighting against quantum mechanics, not because he thought it was mathematically invalid, but because he believed it was incomplete, because something about the picture it painted of reality violated his deepest instincts about what reality should look like. He was losing that fight slowly and publicly. And now, on his 70th birthday, his closest colleague had handed him a proof that his own crowning achievement, general relativity, was equally capable of producing a picture of reality he found philosophically intolerable. Einstein verified the mathematics. He spent time on it, not dismissively, but genuinely, the way you check the work of someone you respect. He found no formal errors. He could not find a step in the proof that failed, a term that was unjustified, an assumption that had been smuggled in without declaration. The solution was internally consistent. The Gödel universe obeyed general relativity exactly. And Einstein's response, documented in the written record and in the recollections of those around him, was essentially this. He accepted the mathematics and hoped it did not apply to the real world. That distinction between mathematically allowed and physically real would become one of the defining fault lines in theoretical physics. Scientists make this distinction constantly and often for good reason. Equations frequently admit solutions that describe situations we have no reason to believe exist. A differential equation describing the flow of water might include a solution with negative density. You discard that solution because it is unphysical. The mathematics allows it, but reality does not seem to. Einstein's response to Gödel was something like this, wrapped in the particular authority of a man who had invented the theory under discussion. He argued that while the Gödelian universe was mathematically consistent, it was not observationally supported. Our universe, as far as anyone could tell, was not rotating in the required way. The stars and galaxies did not show the patterns one would expect if space-time itself were spinning. Therefore, the Gödel solution was, in Einstein's framing, a curiosity rather than a description of anything real. What is extraordinary about this response, in hindsight, is not that it was wrong exactly, but that it established a template that physics would use for the next several decades whenever it encountered the problem of time. The template runs like this. You find a result that calls into question the fundamental nature of time. You verify that the mathematics is sound. You then ask whether the result applies to our specific universe. When you cannot confirm that it does, you file the result in a special category, not refuted, not ignored, but quietly quarantined from the main body of ongoing research. It gets labelled a mathematical curiosity, an edge case, a pathological solution, an interesting but non-physical regime, and everyone moves on. This is not dishonesty. It is not cowardice. It is, in most cases, a perfectly reasonable scientific practice. You cannot chase every mathematically permitted possibility, and without experimental guidance, you need some way to prioritize. But the cumulative effect of this practice, applied again and again to results that question the nature of time, produced something troubling. It produced a physics community that had collectively decided, without ever quite saying so explicitly, that time could be trusted, that it was linear, that it flowed in one direction, that the future was genuinely open and the past was genuinely closed. Not because this had been proved, but because the alternative was uncomfortable and the evidence was not yet strong enough to force a reckoning. Gödel was the first proof that the reckoning was coming. Einstein, unwittingly, had given it its first quiet voice. Part 3. The hidden architecture of the proof. To really understand what Gödel did, you need to sit with the geometry for a moment, because the mechanism is beautiful in the way that the most dangerous ideas often are. It is precise. It is inevitable. And once you see it, you cannot unsee it. General relativity describes gravity not as a force in the Newtonian sense, not as an invisible hand reaching across empty space, but as a geometric property of space-time. Mass curves space-time, and curved space-time tells everything that moves through it, including light, including clocks, including the path of any physical object, how to travel. This is not metaphor. The mathematics says, quite literally, that space and time are woven together into a four-dimensional fabric, that the presence of energy and mass bends and stretches that fabric, and that what we experience as the pull of gravity is simply the tendency of everything to follow the straightest possible path through a curved geometry. Now, Einstein's field equations are not a single equation, but a system of equations, and they are extraordinarily rich. They have many different solutions, each describing a different possible universe. The simplest and most studied solution describes a static, isotropic universe, one that looks the same in every direction. Later solutions described expanding universes, contracting universes, universes with black holes. Each solution is a kind of universe blueprint, specifying the geometry of space-time and therefore the rules by which everything in that universe behaves. What Gödel did was write down a solution in which the universe rotates as a whole. This is harder to visualize than it sounds, because there is no fixed external reference frame from which you could observe the rotation. The rotation is intrinsic to the space-time geometry itself. What it means physically is that the local axes of space and time, what counts as a spatial direction and what counts as the time direction, are not aligned the same way everywhere. They are twisted relative to each other in a systematic global pattern. This is an extension of a phenomenon called frame dragging, which occurs even around ordinary rotating objects in general relativity. A spinning planet or a spinning black hole drags the surrounding space-time around with it, like a spoon stirring honey. Gyroscopes near a rotating mass will precess, not because of any force acting on them, but because space-time itself is being dragged. In the Gödel universe, this effect is not local and bounded. It is global. The entire space-time is in a state of rotation. And here is where the geometry produces its extraordinary consequence. In general relativity, The paths available to physical objects through space-time are constrained by the light cone structure. At every point in space-time, there is a cone of allowed futures. All the directions a physical object or a signal can travel, given that nothing exceeds the speed of light. In ordinary curved space-time, these cones all point consistently toward the future. They may be tilted and distorted by the presence of mass, but they never tip so far over that they begin pointing backward toward the past. In the Gödel universe, the global rotation of space-time causes the light cones to tip progressively as you move in a certain spatial direction. They tip continuously, and far enough from any reference point they have tipped so far that the forward direction of the light cone curves back around to where you started. A path that always stays inside the forward light cone, always pointing toward a locally defined future, can close into a loop. The path is entirely locally causal. Every momentary step is into the local future. But the global structure curves those local steps into a circle. Think about walking in what you believe is a straight line on the surface of a sphere. Locally, at every step, you are walking straight. You are not turning. Your compass says you are heading north, and you stay heading north, but the surface beneath you is curved, and after a long enough journey, you arrive back where you started. Gödel's universe is the four-dimensional temporal version of this. The path is locally causal, locally future-pointing, locally obeying every rule of physics, but globally circular. The past is accessible from the future, not by breaking any law, but by following them all through the right geometry. The thought experiment makes this visceral. You build a rocket. You leave Earth. You travel outward through the Gödel universe, always forward in your local time, never exceeding the speed of light. You set your course along one of these closed, time-like curves. After a long journey, your instruments confirm you have not traveled in a circle spatially. You have moved continuously forward, and then you slow down and land, and you are on Earth. And it is the moment before you left. The people are there. The buildings are there. You are not in a copy of the moment, you are in the moment. The mathematics does not hedge. It does not say in some sense. It says the space-time coordinates of your arrival are identical to the space-time coordinates of your departure. Whether you could actually change anything, whether you could introduce contradictions, whether you would somehow prevent your own departure, these are the questions that have occupied philosophers and physicists ever since. But Gödel was not interested in those questions. His point was simpler and more devastating. Time in a universe obeying general relativity can be structured so that it has no preferred direction. The past is not protected by any fundamental law. The linearity of time, the sense that events march forward in a permanent and unalterable sequence, is not a consequence of the laws of physics. It is at most a property of the particular geometry of our universe, if we have it at all. And here is the question that was already forming at the edges of physics, the one that the Gödel result sharpened into something urgent. If the linearity of time is not fundamental to the laws of physics, what is time actually? Is it a dimension, like space? Is it a direction imposed by the global structure of our particular universe? Is it something that emerges from something deeper? Or is it, in some profound and disturbing sense, not a fundamental feature of reality at all? Gödel had not answered that question. He had made it impossible to avoid. Part 4. The quiet disappearance of a dangerous idea. Gödel's solution was published formally in 1949 in a volume of the Journal Reviews of Modern Physics. Einstein himself contributed an autobiographical essay to the same volume, and in it he acknowledged Gödel's result as an important one that had, in his words, disturbed him considerably. For a man of Einstein's characteristic understatement, this was essentially a declaration of intellectual crisis. And yet the scientific community's response was, by the standards of the result's implications, remarkably muted. There was no formal refutation. No one proved that Gödel had made an error. The solution was acknowledged, discussed briefly in specialist circles, and then quietly classified as what physicists call a non-physical cosmology, a term that functions in practice as a filing cabinet for results that are mathematically valid but that nobody wants to think about too hard. The primary grounds for classification were observational. The Gödel universe requires space-time to rotate globally, and observations of the universe, including the distribution of galaxies and the patterns in the cosmic microwave background, showed no evidence of such rotation. Our universe, to the precision then available, was not spinning. Therefore, Gödel's universe was not our universe. Therefore, at least for practical purposes, you did not need to worry about it. This dismissal was not irrational. Science does not have the luxury of treating every mathematically allowed universe as though it describes the actual one. If it did, the enterprise would grind to a halt under the weight of its own possibilities. But the dismissal did carry a philosophical cost that went largely unacknowledged. It left in place the assumption that time in our universe was reliable, linear, and fundamental, not because this had been established by the failure of any serious alternative, but because the serious alternative that had been raised happened not to match observational data about rotation. The question of what time fundamentally is, whether it is a genuine ingredient of physical reality or something that emerges from or depends on other things, had been successfully avoided rather than answered. Gödel himself did not stop thinking about it. He continued exploring the philosophy of time for the rest of his life, writing privately and publishing occasionally on the subject, arguing in his later work that the relativity of simultaneity in Einstein's theory already suggested that time, as ordinarily understood, as an objective universal flow from past to future, simply did not exist. His argument was that if there is no universal present moment, if what counts as now depends on your reference frame, then the flowing, moving now that we experience is not a feature of the physical world, but of consciousness. The present moment is not found in physics. It is imposed on physics by observers. These ideas, considered eccentric in the 1950s and 1960s, became increasingly difficult to ignore as physics kept encountering the same problem from different directions. Because Gödel's result was not an isolated anomaly. It was, it turned out, the first clear articulation of a question that would resurface again and again at the deepest levels of physical theory. If time was not safe in the universe, Einstein's equations described, how safe was it in the equations describing the quantum world? And what would happen when physicists finally tried to write a single equation describing both? Part 5. When time vanishes from the equation. There is a moment in the history of physics that should have sent shockwaves through every physics department in the world, made headlines in every newspaper, prompted public debates about the nature of reality. Instead, it generated roughly 2 papers in specialist journals and some very uncomfortable conversations at conferences. The moment came in 1967 when 2 physicists, Bryce DeWitt and John Wheeler, wrote down what they believed was the fundamental equation for the quantum state of the universe. The equation they wrote is called the Wheeler-DeWitt equation. It is an attempt to do quantum mechanics to the universe as a whole, to apply the same mathematical framework that describes electrons and photons and atomic transitions to the entire cosmos, to write down a wave function not for a particle, but for everything. This was the beginning of quantum gravity, or at least one attempt at it, the program of unifying quantum mechanics and general relativity into a single consistent theory. And the equation they wrote is extraordinary for one reason above all others. It contains no time variable. Let that register. The equation that is supposed to describe the quantum state of the entire universe, the equation that should, in principle, encode everything about what the universe is and how it evolves, does not include time as a variable. The universe described by the Wheeler-DeWitt equation is not a universe that evolves. It is a static quantum state, a frozen wave function. The universe, from the perspective of this equation, is not going anywhere. It is not changing. It simply is, in a fixed and timeless configuration. And that configuration is everything that exists. Compare this to the Schrödinger equation, which is the standard equation of quantum mechanics for any ordinary system. A particle in a box, an atom in an electromagnetic field, a molecule vibrating in a crystal. The Schrödinger equation has a time derivative on one side. It explicitly describes how the wave function of a system changes over time. The time variable is not just present, it is load-bearing. It is the central organizing axis of the whole equation. Remove time from the Schrödinger equation, and the equation stops making sense. It no longer describes evolution. It no longer describes dynamics. It becomes a statement about a static condition rather than a process. The Wheeler-DeWitt equation has no such term. The time derivative is absent. The equation is of the form h b psi equals 0, where h is the Hamiltonian operator representing the total energy of the universe and psi is the wave function of the universe. An equation that equals 0. The universe in this formulation has 0 total energy and no time evolution. It sits, it is, and within that frozen totality somehow we perceive change. We experience motion and growth and decay and memory and anticipation. Somehow, within a timeless wave function, observers like us encounter a vivid, compelling, undeniable sense of time passing. This is not a peripheral issue. This is not a technical detail to be resolved by a better approximation or a more sophisticated calculation. This is a foundational crisis. The Wheeler-DeWitt equation was derived not by mistake or by carelessness, but by attempting to do something that every physicist agreed needed to be done, namely applying quantum mechanics to gravity. And the result of that attempt was an equation in which the universe has no clock. The same question Gödel raised from the direction of curved space-time and rotating universes now arose again from the direction of quantum mechanics. Where is time? Part 6. The problem of time crisis. The technical name for what emerged from the Wheeler-DeWitt equation is, fittingly, the problem of time. It is a problem, and it is about time. And in the community of physicists who work on quantum gravity, it is widely considered to be one of the central unsolved problems in all of theoretical physics. What makes it particularly alarming, intellectually speaking, is not just that it is unsolved, but that it seems genuinely hard, in the sense that every approach to solving it runs into its own catastrophic difficulty before it gets very far. Here is the core of the problem. Quantum mechanics, as ordinarily formulated, requires time. The Schrödinger equation evolves a quantum state through time. Probability amplitudes for different outcomes are defined with respect to a time parameter. The very notion of measurement, of asking what value a quantum system has for some observable, presupposes that the measurement happens at a particular time. Quantum mechanics without time is like a sentence without a verb. It may contain nouns and adjectives and all sorts of rich information, but it cannot describe anything happening. General relativity, on the other hand, does not treat time as a fixed background. It treats time as part of the dynamical structure of space-time, something that is bent and curved and warped by the distribution of matter and energy. In general relativity, asking "what time is it?" does not have an absolute answer. It depends on where you are, how fast you are moving, what gravitational field you are in. Time is not a universal coordinate. It is a local, relational, contingent property of your position in space-time. When you try to combine these two theories, the quantum and the gravitational, into a single unified framework, these two incompatible treatments of time come into direct conflict. Quantum mechanics says time is an external fixed parameter with respect to which quantum states evolve. General relativity says time is an internal dynamical relative quantity that has no fixed form independent of the geometry of space-time. When you try to write down a theory that is both quantum mechanical and generally relativistic, you get the Wheeler-DeWitt equation, and in that equation time has disappeared because it was squeezed out in the collision between these two incompatible conceptions. Physicists have tried many approaches to rescue time from this equation. Some have proposed internal clocks, physical degrees of freedom inside the universe that could serve as a substitute time variable. The idea is that even if there is no external time, some internal variable, perhaps the volume of the universe or the value of a scalar field, might increase monotonically and serve as a clock against which other things change. This is called relational time, and it is genuinely clever, but it runs into a serious difficulty. There is no unique choice of internal clock. Different choices give different physics. The theory becomes ambiguous in a way that seems fundamental rather than technical. Others have proposed that time emerges thermodynamically, that the arrow of time, the sense in which one direction is the past and the other is the future, is a consequence of increasing entropy rather than a fundamental feature of the laws themselves. This is an old idea with roots in the work of Boltzmann and the thermodynamics of the 19th century, but recent versions have been made more precise by the physicist Carlo Rovelli, among others. In Rovelli's thermal time hypothesis, time as we experience it is not the fundamental time of physics, but a thermal statistical phenomenon, the direction in which entropy increases in the particular physical state we happen to find ourselves in. If this is right, then time is not a basic ingredient of the universe. It is something like temperature, a useful emergent description of a large-scale statistical behavior. None of these approaches has achieved consensus. None has been experimentally confirmed or refuted. Each resolves one part of the problem of time and creates new problems elsewhere. The situation in quantum gravity today is not one where physicists know what time is, but disagree about the details. The situation is one where the most fundamental equations available provide no agreed-upon account of time at all. Time is either emergent, relational, thermal, or observer-dependent, depending on which approach you find most compelling, and there is currently no experiment that can distinguish between them. The most basic feature of your experience, the feeling that you exist within a forward-moving sequence of moments, has no agreed-upon physical basis. Gödel showed that the laws of gravity allow universes without linear time. The Wheeler-DeWitt equation showed that the laws of quantum gravity may not contain time at all, and the trail of broken solutions and competing frameworks has only made the question louder with each passing decade. Part 7. The block universe becomes serious physics. Einstein had actually seen this coming, not the Wheeler-DeWitt equation specifically, but the general direction of travel. Special relativity, his first great theory, had already struck a blow against the common-sense picture of time back in 1905, and it had done so with a quiet precision that people are still unpacking over a century later. The blow was this. In special relativity, there is no universal present moment. Two observers moving relative to each other will disagree in a precise and calculable way about which events in distant locations are happening simultaneously. This is not an imprecision of measurement. It is not because their clocks are imperfect or their light signals take time to travel. It is structural. The laws of physics do not single out any particular moment as the universal now. The present is observer-dependent. This led physicists like Hermann Minkowski, working in the early 20th century, to propose a picture of reality called the block universe. In the block universe, time is treated as a fourth dimension, analogous to the three dimensions of space. Past, present, and future all exist with equal ontological status. Nothing is created when a moment arrives or destroyed when it passes. The universe is a four-dimensional structure, all of its temporal extent existing simultaneously in the mathematical description, and what we call the flow of time is simply our experience of traversing that structure from one end to the other, like a camera moving through a finished film strip. In the block universe picture, every event that ever happened or ever will happen already exists, in the only sense that matters for physics, as a coordinate in four-dimensional space-time. Your birth and your death are both there. The formation of the solar system and its eventual engulfment by the dying sun are both there. The distinction between past and future is a perspective distinction, not an ontological one. The future is not empty and unwritten. It is there in the block, fixed and definite, waiting only in the sense that you have not yet traversed it. Gödel found this picture deeply compelling, and in his philosophical writing argued that special relativity alone already demolished the reality of time as ordinarily conceived. If there is no universal now, then the flowing present that defines our experience of time cannot be a feature of physical reality. It must be something else, something that experience adds to a physics that does not contain it. And when you add general relativity's rotating universe to the block universe picture, you get something even stranger. Not only does every moment exist, but in the right kind of universe, the geometry of the block can curve back on itself, allowing paths through it that loop through the same moment from multiple directions. The block becomes not just a static four-dimensional structure, but a potentially self-intersecting one. A structure where the very concept of a direction you can call forward might not be globally defined. Modern physicists working on quantum cosmology have taken the block universe picture increasingly seriously, not as metaphysics, but as a straightforward reading of what their equations say. The wave function of the universe in the Wheeler-DeWitt formalism is most naturally interpreted as a timeless block. It does not evolve. It is not a function of time. It is a function on the space of all possible three-dimensional geometries, what physicists call superspace. And the universe is just a point in that space, not a trajectory through it. If this is correct, the universe does not have a history in any fundamental sense. It simply is a configuration, and history is what observers embedded in that configuration experience as they process information and form memories. Part 8, the first crack in reality's clockwork. The fragmentation of ideas about time in modern theoretical physics is not a sign that physicists are confused, or that the field is in crisis in the usual sense. It is a sign that the problem is genuinely hard, and that the question of what time is has resisted resolution despite being attacked by some of the most brilliant minds in the history of science. There are now at least 4 serious, mathematically developed approaches to time in the context of quantum gravity, and they give genuinely different answers about what time is and whether it exists at any fundamental level. There is the relational approach, developed most fully by Carlo Rovelli and Lee Smolin in the context of loop quantum gravity, where time does not exist as a background or a fundamental parameter. Instead, physical quantities are defined only in relation to other physical quantities. There is no time. There is only change. The change of one physical variable relative to another. The universe does not evolve in time. The universe is a network of correlations between events, and what we call time is our experience of navigating that network. There is the emergent thermodynamic approach, where time arises from the statistical mechanics of large numbers of degrees of freedom, essentially from entropy and its tendency to increase. In this view, the arrow of time is not fundamental but statistical, and the deepest laws of physics are time-symmetric, Past and future are not built into the laws. They emerge from the asymmetric initial conditions of the universe, from the fact that the universe started in an extraordinarily low entropy state and has been climbing toward equilibrium ever since. There is the many worlds approach, where time is defined by decoherence, by the branching of the universal wave function into classically distinct branches, and where the apparent flow of time is the experience of finding yourself on one particular branch as it splits from others. And there are approaches connected to string theory and holography, where time, in some descriptions, is emergent from a lower dimensional theory that has no time variable at all. What all of these approaches share is the recognition that time, as a fundamental, universal, absolute parameter, is not something that physics can currently justify. The equations keep finding ways to dissolve it, to reduce it to something else, to derive it rather than assume it. Gödel's rotating universe was the first clear formal demonstration that time was not on solid ground. Every decade since has produced new evidence that the ground was even less solid than he thought. Part 9, the Kerr black hole revelation. In 1963, a New Zealand mathematician named Roy Kerr did something that had been staring at physicists for nearly 5 decades. He solved Einstein's field equations for a rotating black hole. The Schwarzschild solution, worked out in 1916 while its author was serving in World War I, described a non-rotating black hole, a perfectly spherical object with a singularity at the center and an event horizon defining the point of no return. It was a clean, elegant solution. But real astrophysical objects spin. Stars spin. The matter that collapses to form a black hole carries angular momentum. Whatever that collapsed matter becomes should spin too. It took until 1963 for anyone to write down the actual geometry. The Kerr solution was more complicated and more disturbing than its non-rotating predecessor. Around a rotating black hole, the geometry of space-time exhibits frame dragging in an extreme form. The space-time around the black hole is being dragged in the direction of rotation, like water spiraling into a drain. You cannot sit still near a Kerr black hole, even outside the event horizon, even in a region where you could, in principle, escape. The geometry itself is dragging you around. If you try to stand still relative to the distant stars using arbitrarily powerful rockets, you simply cannot. The rotation of space-time overrides you. This region, outside the event horizon but inside the static limit, where the dragging becomes irresistible, is called the ergosphere. But the more unsettling feature of the Kerr solution is what lies deeper inside the event horizon. The Schwarzschild black hole has a singularity at its center, a point where space-time curvature becomes infinite and physics breaks down. The Kerr black hole has a more complex interior structure. The singularity, instead of being a point, is a ring, and the interior structure includes regions that have a familiar character to anyone who has been following this story carefully. Inside the inner horizon of the Kerr black hole, the mathematics predicts the existence of regions where closed time-like curves become possible. The same structures Gödel found in his rotating universe appear again in the interior of a rotating black hole. The mechanism is similar in both cases. Rotation, extreme enough and structured in the right way, warps the light cone structure of space-time so severely that forward-pointing time-like paths can close into loops. The Gödel universe achieves this through global rotation. The Kerr black hole achieves it through the extreme local curvature and rotation near the ring singularity. Whether any physical observer could actually reach these regions is a separate question. The inner horizon of a Kerr black hole is thought to be unstable under small perturbations, meaning that any infalling matter or radiation would likely cause it to collapse into a singularity before the closed time-like curve regions could be reached. and anything that crosses the outer event horizon is, of course, causally disconnected from the universe outside for all practical purposes. But the mathematical fact remains. The equations that describe our universe, applied to the kinds of objects we believe exist in our universe based on astrophysical observations, produce space-time structures containing closed time-like curves. The Gödel universe was not an isolated freak solution. It was a preview of a pattern. Rotation appears to be the key. In Gödel's universe, global rotation of space-time produces closed time-like curves. In Kerr black holes, local extreme rotation of a collapsed mass produces closed time-like curve regions. In both cases, the physics is locally consistent. Every individual piece of the solution obeys every law. It is only the global structure, the way all those locally valid pieces fit together, that produces the time loop geometry. And this pattern, rotation as a catalyst for temporal breakdown, turns out not to be coincidental. It reflects something deep about the relationship between angular momentum and the causal structure of space-time that is still being worked out in modern theoretical physics. The black hole at the center of our galaxy, Sagittarius. A star is a rotating black hole. The supermassive black holes at the centers of active galaxies are rotating, some of them at very close to the theoretical maximum spin rate. Every stellar mass black hole formed by the collapse of a rotating star carries that rotation into its final state. Kerr black holes are not exotic theoretical objects. They are what the universe produces when massive stars die. The Kerr solution is not a curiosity. It is likely the correct description of the majority of black holes in existence. And the Kerr solution contains, buried in its mathematics like a time capsule from Gödel, the same geometric signature. Extreme rotation breaks temporal ordering. Part 10, Wormholes and Time Engineering. The possibility that space-time geometry could be, in principle, more flexible than ordinary experience suggests did not stay confined to the abstract mathematics of rotating universes and black hole interiors. In the late 1980s, the physicist Kip Thorne, working with his graduate student Mike Morris, and later with Ulvi Yurtseva, explored what it would mean to have a traversable wormhole, a tunnel through space-time connecting two distant regions. This was not entirely new territory. Wormhole-like structures had appeared in solutions to Einstein's equations since the 1930s, but they were uniformly non-traversable, either collapsing too fast for anything to pass through or requiring you to travel faster than light to use them. The Morris-Thorne wormhole was different. By allowing the throat of the wormhole to be threaded with what physicists call exotic matter, material with negative energy density, a physically unusual but not thermodynamically forbidden substance, they showed you could, in principle, keep the throat open long enough for something to pass through. This was already strange enough. But the real shock came when Thorne and Yurtseva worked out what happens if you take the two mouths of such a wormhole and put them through different gravitational fields, or accelerate one of them to a high velocity and then bring it back. Special relativity tells us that clocks tick at different rates depending on how fast they move. Accelerate one wormhole mouth and then slow it back down, and that mouth will have accumulated less proper time than the other. If both mouths started synchronized, they are now offset in time. And since you can pass through the wormhole from one mouth to the other, and the wormhole is a shortcut through space that takes essentially no time to traverse, you now have a tunnel connecting two moments in time, as well as two places in space. A traveller could enter one mouth at what was, by the external universe's clocks, a later time, and emerge from the other mouth at an earlier time. The wormhole becomes a time machine. This is not a science fiction scenario invented for narrative convenience. It is a direct and formally correct result of applying general relativity to a physically allowed configuration. at least if you allow exotic matter. The construction shows once again that time as a forward-directed, non-reversible flow is not protected by the laws of physics. General relativity permits space-time geometries in which the past is reachable, and the mechanism is not magic or contradiction. It is geometry. The catch, and it is a significant catch, is the exotic matter requirement. Negative energy density material is not something we have ever created or observed in macroscopic quantities. Quantum field theory does permit negative energy densities in certain quantum states, the Casimir effect between closely spaced conducting plates being the most famous example. But the amounts involved are minuscule, and whether they could ever be concentrated and manipulated at the scale required for a traversable wormhole is entirely unknown. Most physicists consider it practically impossible and possibly fundamentally forbidden. The wormhole time machine remains a purely theoretical construction, but the theoretical point it establishes is real and important. The laws of physics, as we understand them, do not forbid the past being accessible. They may impose practical limits that are, for all engineering purposes, infinite. But the fundamental prohibition that common sense expects to find is not there. Part 11. Hawking's attempt to save time. Stephen Hawking was deeply uncomfortable with all of this, not with the mathematics, which he had contributed to more than almost anyone, but with the implications. In 1992, he proposed what he called the chronology protection conjecture, a formal statement of his belief that the universe conspires to prevent closed time-like curves from forming in any physically realizable situation. The conjecture was not derived from any existing theory. It was a hypothesis, an educated guess motivated by Hawking's intuition that a universe with closed time-like curves would be so paradox-ridden, so causally incoherent, that nature must somehow forbid them. The proposed mechanism was quantum. In any space-time region where a closed time-like curve was about to form, quantum vacuum fluctuations would diverge, creating an enormous energy density that would destroy the region before the loop could complete. The idea was plausible and has some support from particular calculations in semi-classical gravity, but it has never been proven. And there are competing arguments from string theory and loop quantum gravity and other frameworks that suggest the conjecture may be too strong, that quantum gravity may actually permit some form of causal loop under sufficiently exotic conditions. What the chronology protection conjecture reveals, more than any specific physical prediction, is the degree to which physicists felt the need to actively argue for the safety of time. The conjecture exists because the default state of general relativity is to generate solutions containing closed time-like curves whenever the geometry becomes extreme enough, and someone needed to argue that physics would step in to prevent them. The very need for such a conjecture is an acknowledgement of how fragile temporal order looks in the equations. You do not need a conjecture to protect things that are robustly protected. The chronology protection conjecture is, in its way, a monument to the instability of the linear time picture. Part 12. The Return of Gödel's Ghost. The Gödel universe is not a lonely anomaly in the mathematical space of solutions to general relativity. Over the decades, physicists and mathematicians exploring the full solution space of Einstein's field equations have found that time pathological solutions, solutions containing closed time-like curves, are not rare. They are not even particularly exotic. They appear naturally whenever the geometry of space-time becomes extreme in certain ways. When rotation is fast enough. When topology is non-trivial. When matter distributions create the right kind of lensing and focusing of light cones. Beyond Gödel and Kerr, there are solutions like the Tipler cylinder, an infinitely long rotating cylinder whose exterior spacetime permits closed time-like curves for anyone orbiting it. There are the Van Stockham solutions, rotating dust clouds that produce the same effect. there are solutions involving cosmic strings under tension. There is Misner space, with closed time-like curves arising purely from the topology of the manifold rather than from any matter distribution. In each case, the mechanism is different. In each case, the conclusion is the same. The geometry allows paths that return to their own past. What this proliferation of time pathological solutions tells us is something that Gödel intuited but could not fully articulate in 1949 with the mathematical tools available. Temporal linearity, the property of space-time that ensures the future is distinct from and unreachable from the past, is not encoded in the field equations of general relativity as a general principle. It is a property that holds in particular solutions under particular conditions. It is, in a precise technical sense, a contingent feature of the kind of space-time we happen to inhabit, not a necessary consequence of the laws governing space-time in general. The Gödel solution was the first brick in a wall that has been built gradually, without any single dramatic breakthrough, across more than 7 decades of research. The wall, if you step back far enough to see it whole, separates 2 things: the laws of physics on one side, and the linear temporal structure we assume those laws demand on the other. The laws do not in fact demand it. They permit it in the sense that many solutions possess it, but they also permit its absence, and the solutions lacking it are numerous, mathematically natural, and in some cases physically relevant. Gödel was not describing an impossible fringe universe. He was pointing at a feature of the equation space that physics has been systematically rediscovering ever since. Part 13, the most precise clocks ever built. You might be tempted to think that all of this is a problem of the very large and the very exotic, of rotating universes and black hole interiors and hypothetical wormholes that require matter physics cannot produce. You might think that at the human scale, in the lab, time is fine. Time is steady and reliable and behaves exactly as expected. That temptation is understandable, and it turns out wrong in ways that are increasingly difficult to ignore. The most precise clocks ever built are not the cesium atomic clocks that have defined the second since 1967. They are a newer generation of devices called optical lattice clocks, developed at institutions like the National Institute of Standards and Technology, known as NIST, and JILA in Boulder, Colorado, over the past 2 decades. These clocks use the transition frequencies of atoms like strontium or ytterbium, which oscillate at optical frequencies, meaning hundreds of trillions of times per second, rather than the microwave frequencies of cesium clocks. The result is a timekeeping precision so extreme that it is difficult to convey through ordinary analogy. But an attempt, the best optical lattice clocks would lose or gain less than 1 second in roughly 300 million years, an error rate expressed as something like 1 part in 10 to the 19th. To put that differently, if you had started such a clock at the moment the universe cooled enough for atoms to form, roughly 380,000 years after the Big Bang, that clock today would be off by less than a fraction of a microsecond. The precision is not just impressive for engineering reasons. It is scientifically dangerous for philosophical ones, because these clocks, operating at this level of precision, can directly measure gravitational time dilation over vertical distances of centimeters. In general relativity, clocks run faster in weaker gravitational fields and slower in stronger ones. This is not a large effect at human scales. On the surface of the Earth, the difference in gravitational potential between the floor and the ceiling of a typical room corresponds to a time dilation of roughly 4 parts in 10 to the 17th per meter of height. For any ordinary clock, this is far too small to detect, but for an optical lattice clock, it is detectable. NIST researchers have confirmed that a clock sitting 33 centimeters higher than an identical clock ticks measurably faster. The effect is real. it is in the laboratory, and it means that time is not uniform even across the height of a human body. What this tells you, once you sit with it, is that time is not a background. It is not a uniform, featureless medium in which events occur. It is a physical quantity that responds to other physical quantities, specifically to the distribution of mass and energy in its vicinity. Time is more like temperature than like an empty stage. Just as temperature varies from place to place, depending on what physical processes are occurring, time varies, or rather, its rate of passage varies, from place to place depending on the local gravitational field. In regions of stronger gravity, time runs more slowly. In regions of weaker gravity, it runs faster. This is not new as a prediction. Einstein predicted it in 1915, but being able to measure it in a tabletop experiment, to put two clocks on a lab bench separated by the length of a forearm and watch them disagree about how fast time passes, transforms it from a theoretical result into an empirical reality about the texture of time at human scales. And if time can vary across 33 centimeters of vertical distance, what exactly are we measuring when we measure it? We are not measuring the passage of some universal external parameter. We are measuring a local property of space-time, a property that depends on where you are, what is around you, and how fast you are moving. Time is environmental. Time is relational. Time is, at minimum, not what Newton thought it was, and very possibly not what common sense supposes it to be. The implications of this for the question Gödel raised are not immediate, but they are real. If time is a physical, measurable, locally variable quantity that responds to the geometry of space-time, then the question of what time fundamentally is, whether it is real, whether it is emergent, whether it exists independent of observers, is not a purely philosophical question. It is an experimental one. And the experiments being run on optical lattice clocks today are beginning to probe that question in ways that were not possible even a decade ago. Part 14, Time Reflection Experiments. Physics laboratories have also, in the past few years, been doing something conceptually strange with time that deserves attention, not because it demonstrates time travel in any dramatic sense, but because it probes the physical status of time's direction in ways that connect directly to the central question of whether temporal linearity is fundamental. Researchers working with specially engineered materials called metamaterials have demonstrated a phenomenon called temporal reflection. The standard understanding of wave reflection is spatial. A light wave or a sound wave or an electromagnetic pulse traveling through a medium encounters an interface, a boundary where the properties of the medium change abruptly in space, and part of the wave reflects backward. This is the physics of mirrors and echoes. Temporal reflection is the time analog. Instead of an interface that is abrupt in space at a fixed time, you create an interface that is abrupt in time at a fixed space. The properties of the medium change suddenly and uniformly everywhere at once. And when a wave is present in that medium at the moment of the change, part of it reflects backward in time. The phrase reflects backward in time sounds more dramatic than the actual physics warrants, and it is important to be clear about what this does and does not mean. The wave is not traveling to the past. The photons or electromagnetic oscillations involved are not going backward through time. What happens is more subtle. The wave reverses its temporal behavior. Its phase evolves in the opposite direction. The effect is real, experimentally confirmed, and geometrically fascinating. But it is a manipulation of wave behavior within a medium, not a demonstration of macroscopic time reversal. What it is, however, is a direct demonstration that the direction of time's arrow is not always imposed rigidly on physical processes by the underlying laws. In most familiar situations, wave propagation has a clear directionality, a sense in which it moves forward in time in a particular way. Temporal reflection techniques show that this directionality can be manipulated in controlled laboratory settings. The direction of time's arrow in wave dynamics is, in some sense, a property of the medium and the boundary conditions rather than an absolute constraint imposed from outside. This is consistent with the broader picture emerging from quantum gravity and thermodynamics, in which the arrow of time is not fundamental but emergent. The experiments do not prove that picture, but they provide a kind of existence proof for time direction effects that are controllable and system-dependent rather than universal and imposed. Part 15, when cause and effect become optional. The most philosophically disorienting experiment that modern physics has produced in the area of time and causality does not involve black holes or cosmic rotation or exotic matter. It involves a quantum optical device called a quantum switch, and it has been implemented in real laboratories with results that have been reproduced multiple times since 2015. The quantum switch is a device in which a quantum system acts as a control for the order in which two operations are applied to another quantum system. In a classical world, you could apply operation A before operation B, or B before A, and the order would be definite. You would know which happened first. In a quantum switch, the order is placed in superposition. The operations occur in a state that is a quantum superposition of A before B and B before A simultaneously. This is not merely saying that you do not know which came first, the way you might not know which side of a coin has landed if you have not looked. In quantum mechanics, superposition means both states are genuinely simultaneously real in the relevant sense. The quantum switch is not in an unknown order, it is in an indefinite order, a state that has no classical analogue. And experiments have confirmed that this indefinite causal order is genuinely physical. You can perform measurements that demonstrate the superposition is real, that neither order was the actual order, in the same sense that a particle passing through a double slit has genuinely passed through both slits simultaneously until it is measured. The implications for time are significant. Causality, in the ordinary sense, requires temporal order. A cause is B means A happens first, and A's occurrence is part of the causal chain that produces B. If A and B occur in an indefinite order, if neither precedes the other in any objective sense, then the causal relationship between them becomes ambiguous in a way that feels radical. What does it mean for one thing to cause another if there is no fact of the matter about which came first? Advocates of the indefinite causal order interpretation argue that we are discovering that causality is an emergent concept, something that holds approximately and robustly in the classical regime, but breaks down at the quantum level, just as temporal ordering does. Causality, like time itself, is not fundamental. It is an effective description that works well in the classical regime, but dissolves when you look closely enough at the quantum structure of reality. This directly echoes what the problem of time and the Wheeler-DeWitt equation tell us from the quantum gravity direction. Time and the causal ordering that time makes possible are features that emerge from the physics rather than being built into it at the foundation. The quantum switch experiments are not about cosmological scales or extreme gravitational fields. They are happening in optics laboratories with equipment that fits on a table. The dissolution of temporal order is not a feature only of the extreme. It is a feature of the fundamental. Part 16, the clocks that do not agree with reality. There is one more experimental thread worth pulling, and this one operates at the opposite end of the scale from everything we have discussed so far. Not a tabletop clock, not a quantum optics lab, not the interior of a rotating black hole. This thread stretches across the entire observable universe, across 13.8 billion years of cosmic history, and it hints that even the largest scale structure of time, the timeline of the universe as a whole, may not be as settled or as simple as cosmologists once believed. The problem has a name. Physicists call it the Hubble tension, and if you have not heard of it, that is partly because it is the kind of result that cosmology would very much prefer to quietly resolve before making too much noise about it. The Hubble constant is the number that describes how fast the universe is currently expanding, how quickly galaxies are receding from each other as space itself stretches between them. It is named after Edwin Hubble, who first measured the expansion of the universe in the 1920s and gave cosmology its central organizing fact. For nearly a century, measuring the Hubble constant accurately has been one of the primary goals of observational cosmology. We have poured enormous resources into it. We have launched space telescopes specifically to pin it down. And the answer we keep getting is that the universe cannot seem to agree with itself about what the answer is. Here is the specific problem. There are two fundamentally different ways to measure the Hubble constant, and they use entirely different physics, look at entirely different epochs of cosmic history, and rely on entirely different physical phenomena. The first method uses the cosmic microwave background, the faint afterglow of the Big Bang itself. This is the oldest light in the universe, radiation that has been travelling toward us since roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and space became transparent for the first time. The patterns in this microwave background, the subtle variations in temperature across the sky, encode a precise snapshot of the early universe's geometry, composition, and dynamics. When cosmologists analyze those patterns using the standard model of cosmology, they can extrapolate forward to predict what the Hubble constant should be today. The answer they get is approximately 67 kilometers per second per megaparsec. That is the number that tells you how fast a galaxy 1 megaparsec, about 3.26 million light-years, away is receding due to cosmic expansion. The second method builds what astronomers call a cosmic distance ladder, a series of overlapping measurement techniques that carry you from nearby stars outward to the most distant observable galaxies. The rungs of this ladder include Cepheid variable stars, which pulsate at rates directly related to their intrinsic brightness and can therefore serve as reliable distance markers, and Type 1a supernovae, the spectacular explosions of certain white dwarf stars that always reach approximately the same peak luminosity and can therefore be used as what astronomers call standard candles, objects whose true brightness is known so that their apparent brightness reveals their distance. When you use this distance ladder to measure the local expansion rate of the universe directly, the answer you get is approximately 73 kilometers per second per megaparsec. 67 versus 73, a difference of roughly 9%. Now, 9% sounds like a rounding error. It sounds like the kind of discrepancy you would shrug at in everyday life. The difference between estimating a crowd at 1,000 people and someone else estimating 1,100. But in modern cosmology, where measurement precision has been refined over decades to extraordinary levels, a 9% discrepancy between two independent methods is not a rounding error. It is a screaming alarm. The statistical significance of this disagreement has grown with each passing year, as both measurements have become more precise, and it now sits at a level where the probability of it being a coincidence or a random fluctuation is essentially negligible. Something is genuinely wrong somewhere. The two measurements are not converging. They are not getting closer as precision improves. If anything, the tension is hardening. The possible explanations span a range from the mundane to the revolutionary. On the mundane end, there could be subtle systematic errors in one or both measurement techniques, calibration problems in the distance ladder, unknown biases in the selection of Cepheid stars or supernovae, small corrections that have been applied incorrectly or not at all. Astronomers have spent years hunting for these errors, and and they have found and corrected several. The tension has not gone away. On the revolutionary end, the discrepancy might be telling us that our standard model of cosmology is incomplete in a fundamental way. Perhaps dark energy, the mysterious component that makes up roughly 68% of the universe's energy budget and drives the accelerating expansion, is not a cosmological constant with a fixed, unchanging value, as the standard model assumes. Perhaps it evolves over cosmic time, changing its strength or its character as the universe ages. If dark energy was different in the early universe than it is today, then the standard model's prediction of the Hubble constant from the cosmic microwave background would be wrong in a systematic way, and the true expansion rate today might be closer to the locally measured value of 73. Or perhaps the discrepancy points to new physics in the early universe, some undiscovered particle or field or interaction that was active in the first 100,000 years of cosmic history and has since faded, leaving a subtle but measurable imprint on the expansion history. There are dozens of proposed models in this category, collectively called early dark energy models, and while some of them can reduce the Hubble tension, none of them eliminate it completely while remaining consistent with all other cosmological observations. The problem is genuinely resistant to easy solutions. What this means in the context of everything we have been discussing is this. When you try to measure time at the largest possible scale, when you try to reconstruct the timeline of the entire universe from its first fraction of a second to the present day, the universe hands you two answers that do not agree. The cosmic clock, if you want to call it that, the record of how time has passed since the Big Bang and how fast space has expanded through that time, is not giving a consistent reading. It is not that we lack the precision to read it, we have extraordinary precision. The problem is that the universe, read from different perspectives using different physical phenomena, tells different stories about its own history. This does not slot directly into the problem of time in the technical sense that the Wheeler-DeWitt equation does, or the way that closed, time-like curves in rotating black holes do, but it sits in the same family of results. The family of discoveries where time, examined carefully, resists being what we need it to be. At the smallest scale, optical lattice clocks show that time varies across the height of a human being. At the quantum scale, indefinite causal order experiments show that temporal sequence can be genuinely undefined. At the cosmological scale, the Hubble tension shows that even the universe's own expansion history, its record of how time has passed since the beginning, cannot be consistently determined from different vantage points. The pattern, when you pull back far enough to see it, is not subtle. Every time physicists try to nail down what time actually is, every time they try to measure it precisely enough, or theorize about it deeply enough, it does something unexpected. It bends. It vanishes from equations. It loops back on itself in rotating geometries. It becomes indefinite. In quantum systems, it refuses to give a consistent answer about the age and history of the universe. Time does not behave like a solid, reliable background. It behaves like something that is not quite fully there. Something that is partly real and partly constructed, partly fundamental and partly emergent, partly external and partly something that observers like us are quietly generating from the inside. The problem of time is not confined to the exotic or the theoretical. It is showing up in every direction physicists look. And the question Gödel was circling in 1949, the one Einstein hoped would never find an answer, is now being asked not by one equation or one experiment, but by all of them at once. Part 17, the observer problem. Every measurement has a cost, not in the philosophical sense, not as a metaphor about the price of knowledge or the burden of awareness, but as a precise, quantifiable, experimentally verified physical fact. In 1961, A physicist and information theorist named Rolf Landauer published a result that most people outside the physics of computation have never heard of, and which turns out to be one of the most quietly profound statements about the nature of time and observation ever written down. Landauer's principle states that erasing a single bit of information must dissipate a minimum amount of energy as heat. The exact amount is Boltzmann's constant multiplied by the temperature of the environment multiplied by the natural logarithm of 2. It is a small number at room temperature, absurdly small by everyday standards, something like 3 × 10 to the minus 21st joules. But the principle is not interesting because of its magnitude. It is interesting because of what it reveals about the relationship between information, thermodynamics, and the arrow of time. The reason erasure costs energy is thermodynamic at its root. When you erase a bit of information, you are taking a physical system that was in one of 2 distinguishable states, call them 0 and 1, and putting it into a single definite state. You are reducing the number of possibilities. You are compressing the information content of the system. And the second law of thermodynamics, the law that says entropy never decreases in a closed system, demands that this reduction in one place be compensated by an increase somewhere else. The entropy of the environment must go up. Heat must be released. The universe must become, in a precise and measurable sense, slightly more disordered every time you erase a piece of information. Every deletion, every overwrite, every moment when a memory fades or a record is lost costs the universe something real. Now sit with that for a moment and then take the step that Landauer himself and the physicists who built on his work gradually took. If erasing information generates entropy, what does creating information do? What happens physically when you observe something? When your senses register an event? When your nervous system encodes an experience into the electrochemical architecture of memory, you are writing information into a physical substrate. You are creating a record. And while Landauer's principle strictly applies to erasure rather than writing, the deeper implication is this. Every act of observation, every measurement, every moment of conscious experience that leaves a physical trace is embedded in the thermodynamic structure of the universe. Observation is not a passive, costless, transparent window onto reality. It is a physical process. It has thermodynamic consequences. It is part of the same entropic story as everything else. And here is where this becomes directly relevant to the question we have been circling throughout this entire discussion. The direction of time. What physicists call the arrow of time. The fact that there is a past behind you and a future ahead of you, and that the two feel categorically different, that the past is fixed and accessible through memory, while the future is open and inaccessible, turns out to be inseparable from this thermodynamic story about records and observation. Memory is inherently about the past, not because of any mystical property of pastness, not because the past has some special metaphysical status that the future lacks, but because of entropy. Records are entropic traces. A memory is a low-entropy physical configuration that was created by a high-entropy increasing interaction between an observer and an event. The reason you remember yesterday and not tomorrow is not because yesterday is gone and tomorrow has not happened yet. It is because the physics of record creation runs in the direction of entropy increase, and entropy in our universe increases toward what we call the future. An observer that created no records, that processed information without leaving any physical trace of past states in its current configuration, would have no arrow of time. There would be no before or after for such a system in any operationally meaningful sense. The distinction between past and future is not something such a system could access. Time's direction would be, for it, absent, not slowed, not reversed, not confused, absent. This is not speculation. It follows directly from the thermodynamic analysis of what observation physically is. The physicist Sean Carroll has spent much of his career working through the implications of this argument and his conclusions, shared by a growing number of physicists working on. The foundations of statistical mechanics are stark. The arrow of time is not a dynamical problem. It is a boundary condition problem. The fundamental laws of physics, from Newtonian mechanics through quantum field theory, are either exactly or very nearly time-symmetric. Run the equations forward and they describe the physics we observe. Run them backward and they describe physics that is equally mathematically valid. The equations themselves do not know which direction is the future. They do not prefer one temporal direction over another. The past and the future are, from the perspective of the laws alone, interchangeable. What breaks the symmetry, what gives time its direction, is not a law, but a fact about the specific state the universe happens to be in. Our universe began approximately 13.8 billion years ago in a state of extraordinarily low entropy. The matter and energy that would become everything we see was arranged in a configuration of remarkable smoothness and order, far from the maximum entropy thermal equilibrium that a closed physical system naturally tends toward. Since that moment, the universe has been evolving toward higher entropy, spreading out, mixing, losing structure, moving toward the featureless uniformity of maximum disorder. We are living through that process. Every physical event around us, every star burning hydrogen, every egg breaking, every memory forming, every moment of experience, is a small chapter in the universe's long climb from extreme order toward extreme disorder. And because we are embedded in that process, because we are thermodynamic systems that create records by increasing entropy in the right way, we find ourselves oriented in time. We have memories of the direction the universe came from, the low entropy past, because physical processes naturally leave traces of low entropy initial conditions. You remember your breakfast this morning, not because this morning is metaphysically past, but because the eating of your breakfast left physical traces, electrochemical configurations in your nervous system, patterns that encode that event. Those traces exist because entropy-increasing processes created them. The future, by contrast, leaves no such traces in the present. The physical processes that would be required to create memories of future events would require entropy to decrease, which the second law makes overwhelmingly improbable. We are surrounded by records of the past and not of the future, not because the past is real and the future is not, but because of which direction entropy runs in our universe. In a universe that had started in maximum entropy, in perfect thermal equilibrium, none of this would exist. There would be no low entropy initial state to evolve away from. There would be no thermodynamic gradient to drive the formation of records. There would be no observers. There would be no memories. There would be no arrow of time. The directed, flowing, irreversible time that you experience every moment of your waking life is not a feature of the universe's laws. It is a feature of the universe's initial conditions. Change those conditions, start the universe in a different state, and you change the direction, or the very existence, of experience time. This is the point where the thermodynamic argument shakes hands with everything else we have discussed. Gödel argued, philosophically, in the years after 1949, that time as an objective flow from past to future could not be found in the physics. He came to this conclusion through the relativity of simultaneity, through the absence of a universal present moment in Einstein's theories, through the mathematical demonstration that universes without linear temporal order were perfectly consistent with the laws. He was right, for reasons he may not have fully articulated. The flow of time is not in the physics because the physics is time-symmetric. The flow emerges from the state. It emerges from the entropic situation observers find themselves in. It is not discovered in the equations because the equations do not contain it. It is generated by observers processing information in a low-entropy universe. What you are experiencing right now, the sense of this moment existing, of having come from a past and moving toward a future, of time flowing in one direction with the past behind you and the future ahead, is the experience of being a specific kind of physical system in a specific kind of universe. It is the experience of being an information-processing thermodynamic engine embedded in a cosmos that started in extraordinary order and has been running down ever since. The flow of time is real in every sense that matters for your existence. It shapes everything about what you are and how you experience. Reality. But it is not a property of the universe independent of observers like you. It is, in a precise and literally physical sense, something you are doing, something that thermodynamic systems create by being the kind of thing they are, embedded in the kind of universe this is. Gödel saw that time could not be found in the physics. Landauer showed why. The cost of every observation, the entropy generated by every record, the thermodynamics of memory itself. All of it points toward the same quiet conclusion. Time is not the universe's clock, it is yours. Part 18. The universe without a clock. Return to the Wheeler-DeWitt equation. Because now that we have established what observation actually is physically, what it costs thermodynamically, what it does to the entropy of the universe, and to the experience of time, the equation looks different. It looks less like a technical curiosity and more like a confession. The wave function of the universe in the Wheeler-DeWitt formalism is a function on something physicists call superspace, the mathematical space of all possible three-dimensional spatial geometries. Every conceivable configuration of space, every possible arrangement of matter and energy and curvature that could constitute a three-dimensional universe corresponds to a point in this space. The Wheeler-DeWitt wave function assigns a complex number, a quantum amplitude to each of those points. High amplitude means the configuration is probable. Low amplitude means it is improbable. Zero amplitude means it does not exist in any quantum sense. What the wave function does not do is change. It does not evolve. It is not a function of time. There is no time argument to plug in. You cannot ask what the wave function is at 3 o'clock on Tuesday and compare it to what it was at 3 o'clock on Monday. Those questions are not malformed in the sense of being poorly phrased. They are malformed in the sense of applying a concept, temporal evolution, that the equation simply does not contain. The wave function of the universe is a static object. It sits on configuration space like a landscape sits on a map, assigning heights to locations, not changing from moment to moment, but simply describing a fixed terrain. The universe in this formalism does not go anywhere. It does not do anything. It simply is, frozen in a timeless distribution of quantum amplitudes over the space of all possible configurations of reality. Now ask the question that makes this genuinely strange rather than merely technically unusual. What does this mean for you? You are in this universe. Your brain, your memories, the neurons firing right now as you process these words, the electrochemical traces of every experience you have ever had. All of it is physical structure. It is made of matter. It obeys the same physics as everything else in the universe, which means it is part of a configuration. It is a particular arrangement of particles and fields and geometries that corresponds to a point, or, more precisely, a region in the configuration space that the Wheeler-DeWitt wave function is defined on. Your experience of being alive, of being aware, of having a past behind you and a future ahead of you, of time flowing forward through your days. All of that is encoded in the physical structure of your brain at this moment, and your brain at this moment is part of a configuration to which the wave function assigns an amplitude. Here is what follows from this. In a universe described by a timeless wave function, the experience of time passing is not something that gets added to the physics from outside. It is not something that requires time to be fundamental in order to exist. The experience of temporal flow is itself a feature of certain configurations. Specifically, it is a feature of configurations that contain observers. Physical structures complex enough to store records of past states, form models of future states, and process the difference between the two. Those configurations, the ones containing beings that remember and anticipate and perceive duration, appear within the timeless wave function as perfectly ordinary amplitudes. They are just points in configuration space, no more special mathematically than any other point. But they are special physically and experientially because they contain, built into their internal structure, everything required for the beings within them to feel time moving. The analogy that captures this most cleanly is a library. Imagine a library so large it contains every possible book, every possible sequence of characters that could be printed on pages of a given length. Most of these books are nonsense, random strings of letters with no coherent meaning, but some of them are tiny. Fraction are genuine narratives. They are histories, stories in which events unfold in sequence, causes produce effects, characters develop across time, moments follow other moments in a logical and consistent chain. Those books contain time in an internal sense. The narrative has a direction. Earlier pages establish conditions. Later pages develop consequences. A character in such a book, if it were somehow aware of its own existence within the text, would experience temporal sequence with full vividness. It would remember what happened on earlier pages. It would have expectations about later pages. It would have a compelling and accurate sense of living inside a story that was going somewhere. But the book itself does not move through time. The library does not change. No external clock ticks as you read from page 1 to page 300. The book simply is, complete and static, existing all at once on the shelf. The temporal structure the character experiences is entirely internal to the text. It is encoded in the relationships between sentences, in the way page 50 refers back to page 12 and sets up page 90. The character's experience of time is real in every sense that matters for the character. But the time being experienced is not a property of the library. It is a property of the book's internal structure. The Wheeler-DeWitt universe is the library. The wave function is the complete collection of books, assigning amplitudes to every possible configuration, the way the library assigns a shelf location to every possible text. The high amplitude configurations are the coherent books, the ones that make physical sense, the ones where the laws of physics are satisfied and matter is arranged in ways consistent with a long causal history. And within those high amplitude configurations, some of them contain observers. Some of them contain beings whose physical structure encodes memories, expectations, and the experience of temporal flow. Those configurations do not exist one after another. They coexist timelessly as values of the wave function on configuration space. But they contain everything required for the beings within them to experience a universe unfolding in time, to feel the difference between past and future, to build physics, to write down the Wheeler-DeWitt equation, and to eventually realize, with a slow creeping sense of vertigo, that the equation they wrote contains no time. The physicist Julian Barber has developed this picture into one of the most sustained and carefully argued research programs in the foundations of physics. Barber's view, laid out in his book The End of Time, published in 1999, and in a series of technical papers stretching back decades, is that what we call the universe is not a process unfolding through time. It is a static structure, complete and timeless, a Platonic realm containing all possible configurations of the universe simultaneously. Barber calls this realm Platonia, a name that is partly playful and partly precise, a reference to the Platonic notion of eternal, changeless mathematical forms underlying the apparent flux of experience. In Barber's framework, what we call moments are not points on a timeline. They are points in Platonia, individual configurations of the universe that each exist in their own right, timelessly, as elements of the static structure. The reason some of these configurations feel like they come before or after others is not that they occupy positions on an external timeline, but that certain configurations contain, in their internal physical structure, records that appear to be traces of other configurations. A configuration containing a brain that remembers eating breakfast corresponds internally to a moment that feels like it comes after the breakfast happened. But the breakfast configuration and the memory configuration do not exist sequentially. They both simply exist, timelessly, in Platonia. The apparent sequence is encoded in the content of the configurations, not in any external temporal ordering. We are not in this picture travelling through time. We are points in Platonia, configurations that happen to carry within their internal structure the vivid and convincing impression of having come from somewhere and of heading somewhere. The memories are real. The expectations are real. The experience of duration and sequence is real in every sense that touches the experience itself. But the movement, the actual traversal from one moment to the next, the sense that time is flowing, that the present is moving, that you are being carried forward through a sequence of events, that part, Barber argues, is the illusion. Not a confusion or a mistake, but a structural feature of the kinds of configurations that contain observers. Observers are, almost by definition, configurations that feel like they are somewhere in the middle of a sequence. That is what it means to be an observer. And configurations that feel like that are, in Platonia, just there, static, complete, already containing every impression of motion and change and temporal flow that the observer within them will ever have. Whether Barber is right in every technical detail is a question that quantum gravity has not yet resolved. There are serious physicists who find the Platonia picture compelling, and serious physicists who find it incomplete or incoherent in certain respects. But the underlying logical move, the recognition that a timeless wave function is perfectly compatible with observers who experience time, that the experience can be internal to configurations rather than imposed by an external temporal parameter, is not a fringe idea. It is one of the mainstream positions in the foundations of quantum cosmology, and it is a position that follows with reasonable naturalness from the most literal interpretation of the equations physicists themselves have written. The equations said there was no time, and then someone looked carefully at what kind of universe an equation like that describes, and found that it was exactly the kind of universe in which beings would arise who were absolutely convinced that there was. Part 19, the Gödel-Einstein paradox revisited. 75 years after that birthday in Princeton, we can look back at the room, at the snow falling outside, at the two men bent over a handwritten proof, and see something that neither of them could fully see from inside the moment. We can see that they were not having an argument about one unusual cosmological solution. They were having an argument about the nature of reality itself. An argument that physics has been conducting ever since in increasingly technical language, with increasingly precise instruments, without ever quite reaching a verdict. Einstein's position, underneath the mathematics, was fundamentally a position about what kind of universe this is. He had spent his entire career believing, with a depth that went beyond methodology into something closer to aesthetic conviction, that the universe was the kind of place that rewarded comprehension, that its deepest truths were objective, independent of who was looking, clean in their structure, and ultimately separable from the messiness of particular observers in particular situations. He called this belief, in various forms, realism. The universe exists independently of us. Its properties are real whether or not anyone measures them. Its structure is there to be discovered, not constructed. And for Einstein, this belief had a specific implication about time. Time had to be real in the objective sense. It had to flow in a direction that was not merely a feature of thermodynamic circumstance or observer-dependent perspective. It had to be, at some level, a genuine feature of the fabric of things. His own theories had been eroding this conviction for decades before Gödel arrived at his door. Special relativity had already removed the universal present. The discovery that simultaneity is relative, that two observers in relative motion genuinely disagree about which distant events are happening at the same time, had demolished the Newtonian picture of a single cosmic clock ticking uniformly everywhere. Einstein knew this. He had worked out the implications himself and had been living with them for 44 years by the time Gödel knocked. But he managed to preserve, within the relativistic picture, a kind of residual faith that while the present moment was not universal, while simultaneity was observer-dependent, the overall causal structure of space-time was still reliable. The past was still the past. The future was still the future. Events still had a definite order in the sense that mattered for causality. The light cone structure of space-time, the mathematical object that encodes which events can influence which other events, was still globally well behaved. Time still pointed somewhere definite. Gödel's proof attacked exactly this residual faith, not by finding an error in Einstein's reasoning, but by finding a solution to Einstein's own equations in which the light cone structure of space-time tips over so far that forward-pointing paths curve back on themselves. In the Gödel universe, there is no globally consistent direction you can call the future. There is no guarantee that causes precede effects in any absolute sense. The causal structure that Einstein's residual faith depended on is simply absent. And because Gödel had built this result from Einstein's own field equations, the demolition was from the inside. There was no external attack to resist. The equations Einstein had written were themselves the weapon. Einstein's response, the hope that our universe was not the rotating kind, was not intellectually dishonest. It was physically reasonable, as we discussed, given the observational evidence about cosmic rotation. But it was also, at a deeper level, a choice to preserve the faith rather than follow the argument. Because the argument Gödel was making was not really about whether our universe rotates. It was about what the equations permit. And what the equations permit tells you something about what those equations assume, about what they build in and what they leave open, about where the foundations are solid and where they are not. The equations of general relativity permit universes without linear time. That is a fact about the structure of general relativity as a theory, independent of which particular solution describes our universe. And a fact like that, about the structure of your most fundamental theory of space-time, is not something you can resolve by pointing to observational evidence about rotation. It is a statement about what kind of thing time is within the framework of that theory. Gödel understood this distinction with the clarity of someone who had spent his career thinking about formal systems and what their structure reveals. His incompleteness theorems were not about any particular mathematical statement being unprovable. They were about what the structure of sufficiently powerful formal systems necessarily contains, what any such system must include, regardless of its specific axioms. The theorems were structural results about the nature of formal reasoning itself, rather than about any particular piece of mathematics. The rotating universe proof had the same character in Gödel's mind. It was not primarily a claim about our universe. It was a structural result about general relativity as a formal system, a demonstration that the theory's structure permits the dissolution of temporal order, which tells you that temporal order is not built into the theory at a fundamental level. For a logician who had already shown that mathematics cannot prove its own consistency, a universe that cannot guarantee the consistency of its own temporal structure, was perhaps not even surprising. It was the kind of result his entire intellectual life had been preparing him to find. He had shown that sufficiently powerful systems contain truths they cannot demonstrate. Now he was showing that the universe's own physical laws contain solutions they cannot order in time. The pattern was the same. Power and completeness purchase incoherence. The richer the system, the more it contains that it cannot fully control. Einstein wanted to live in a universe that was comprehensible in the deepest sense, where the foundations were solid and the structure was clean. Gödel had spent his life demonstrating that the deepest foundations are never quite solid, that clean structures always contain something irreducibly strange at their core, that the most powerful systems are precisely the ones that harbour their own undoing. These were not just different scientific opinions. They were different ways of being in relation to knowledge itself, different intuitions about what the universe owes us in the way of comprehensibility. The paradox they circled that March afternoon in Princeton was not resolved by either of them. It was not resolved by the physics community that politely filed the result as a curiosity and moved on. It was not resolved in the following decade or the decade after that. Instead, it did something more unsettling than getting resolved. It ramified. It sent roots into every corner of theoretical physics and began producing the same fruit from completely different branches of the tree. Quantum gravity produced the Wheeler-DeWitt equation, which described the universe as a timeless wave function with no time variable, arriving at the same timeless destination from the direction of quantum mechanics rather than classical geometry. Rotating black holes, when their full mathematical structure was worked out in the 1960s, produced interiors containing closed time-like curve regions, the same temporal loops Gödel had found in his rotating universe, now appearing inside the kinds of objects we actually believe to exist in enormous numbers throughout the cosmos. Quantum information experiments produced quantum switches demonstrating indefinite causal order, showing that the temporal sequence of events can be genuinely undefined at the quantum level, not unknown, but undefined. A distinction that matters enormously for what it implies about the fundamental structure of time. Precision atomic clocks produced direct laboratory measurements showing that time is locally variable, that it runs at different rates in different gravitational fields, that it is an environmental and physical quantity rather than a universal background, a result predicted by general relativity but now confirmed at the scale of centimeters on a laboratory bench. Cosmological observations produced the Hubble tension, a persistent and growing discrepancy in measurements of the universe's own expansion history, suggesting that even at the largest possible scale, the cosmic timeline is not as consistent or as settled as the standard model assumes. And thermodynamics, approached from the direction of Landauer's principle and the physics of information, produced the conclusion that the arrow of time, the felt directionality of experience from past to future, is a boundary condition feature of the universe's initial state rather than a law of nature, something that depends on where the universe started rather than on how the laws are written. 6 independent lines of inquiry, 6 different theoretical frameworks, 6 different experimental and observational traditions, all of them approached with genuine rigor and without any predetermination of the conclusion, arriving at the same neighborhood. The neighborhood where time is not fundamental, where it is emergent or relational, or observer-generated, or absent from the foundational equations, or locally variable, or globally inconsistent, or some combination of all of these things that no single framework has yet managed to fully articulate. The paradox did not go away. It went everywhere. And the question Einstein hoped would remain safely unanswered, the question of whether our universe is the kind in which time, as we experience it, has any fundamental reality, has become not more distant with the passage of time, but more immediate, more precise, more empirically grounded, and more impossible to look away from than it was on that snowy afternoon in Princeton when a logician handed a physicist a proof, and the physicist went very, very quiet. Part 20, Final Collapse. What if Gödel wasn't wrong? Let us be precise about what has and has not been established, because this is the kind of subject where precision matters more than almost anywhere else. Where the temptation to overstate the case is strong, and the cost of overstating it is the loss of the thing that makes the case genuinely interesting. The genuine case is interesting enough. It does not need embellishment. No experiment has yet definitively proved that time is an illusion in the full philosophical sense, that it does not exist as a feature of reality independent of observers. No one has travelled through a closed time-like curve or confirmed that one exists anywhere in the observable universe. No wormhole has been detected or observed. The Wheeler-DeWitt equation has not been confirmed as the correct and complete framework for quantum gravity, and there are competing approaches, string theory among them, that handle the question of time differently and have not converged on the same timeless picture. The Hubble tension is real and persistent, but may ultimately have a resolution involving systematic measurement errors rather than new physics. The quantum switch experiments are genuine and reproducible, but demonstrating that causal order can be indefinite in a quantum system does not by itself prove that causal order is never real, or that it fails to emerge robustly at the classical scale. Every single piece of evidence we have discussed is, taken individually, suggestive rather than conclusive. Every thread pulled alone could, in principle, be explained away, reinterpreted, or resolved within a framework that leaves time fundamentally intact. That is the honest accounting, and it is important to say it clearly, because the argument that follows is not an argument from proof. It is an argument from convergence. And convergence in science carries a different kind of weight than proof. It carries the weight of pattern recognition across independent frameworks, the weight of the same answer emerging from questions asked in completely different languages, using completely different tools, pointing at completely different phenomena. Single proofs can be wrong. Single experiments can have systematic errors. Single theoretical frameworks can be incomplete or subtly mistaken in their assumptions. But when 5 independent lines of inquiry developed by different communities of researchers using different mathematics and different instruments all arrive in the same neighborhood without any coordination or predetermined conclusion, that is not something you can explain away by finding an error in one of them. The convergence itself is the signal. So here is what the convergence looks like when you lay it out in full. General relativity, approached from the direction of cosmological solutions, the direction Gödel came from in 1949, tells us that time can be absent or looped in a universe that is physically consistent and mathematically valid. The Gödel universe has no temporal contradiction. It obeys the laws. It simply lacks the property we assumed was universal, the property of time pointing unambiguously in one direction. Quantum gravity, approached from the direction of the Wheeler-DeWitt equation, tells us that the most natural attempt to write a quantum mechanical description of the entire universe produces an equation with no time variable. The universe described by that equation does not evolve. It does not change. It simply is. A frozen distribution of quantum amplitudes over configuration space. Quantum information theory, approached from the direction of quantum switch experiments, tells us that causal order, the temporal sequencing of events, can be genuinely indefinite at the quantum level, not merely unknown, but undefined, existing in a superposition of orders that no measurement of the individual events can retroactively resolve into a single definite sequence. Thermodynamics, approached from the direction of entropy, the arrow of time, and Landauer's principle, tells us that the directionality of time, the felt asymmetry between past and future that is the most immediate and intimate feature of conscious experience, is not a law of physics, but a boundary condition, a consequence of the specific low-entropy initial state of our universe, rather than something encoded in the fundamental dynamics. Change the initial conditions and you change or abolish the arrow. The laws themselves are indifferent to which direction time runs. And precision measurement, approached from the direction of optical lattice clocks, accurate to 1 part in 10 to the 19th, tells us that time is not a universal background, but a local, physical, curvature-dependent quantity that varies from place to place in response to the distribution of mass and energy, detectable across distances as small as the length of a human forearm. 5 independent lines, 5 different kinds of evidence, 5 different communities of researchers, most of them not primarily concerned with the philosophical question of time's reality, all producing results that point toward the same unsettling conclusion. Not toward a proof, but toward a question asked with increasing precision and urgency. What justification do we actually have for believing that time, as we experience it, as a universal, forward-flowing, objectively directed medium in which all events occur and which exists independently of any observer, corresponds to anything fundamental in the structure of physical reality? The honest answer in 2025 is that the justification is surprisingly thin. The experience is overwhelming. The justification is thin. 3 broad positions remain live in modern physics, and it is worth being clear about what each of them actually claims, because they are often conflated in popular discussions in ways that obscure the real disagreement. The first position is that time is fundamental, that it is a genuine, irreducible ingredient of physical reality, and that the apparent disappearance of time from our current best equations is a sign that those equations are incomplete rather than a sign that time is not there. On this view, a future theory of quantum gravity, one we have not yet written, will restore time to a central role in the foundations of physics while explaining why our current frameworks seem to lose it. This is a coherent position, and it has serious defenders. Its advantage is that it preserves the common sense picture. Its disadvantage is significant. It requires us to believe that general relativity, quantum field theory, quantum information theory, thermodynamics, and precision measurement are all simultaneously misleading us about something as basic as whether time is fundamental. That is a lot of simultaneous misleading to attribute to our best physical frameworks. It is possible, but it is not obviously the more parsimonious choice. The second position is that time is emergent. On this view, time is real, but not fundamental. It arises from some deeper, timeless structure, the way that temperature arises from the statistical mechanics of large numbers of molecules, or the way that wetness arises from the quantum chemistry of water. Temperature is real. You can measure it. It affects everything, but it is not a fundamental ingredient of nature. It is a useful, accurate, high-level description of what a large collection of molecules is, doing at the statistical level. On the emergent time view, time is like this. It is a real and useful description of patterns in a fundamentally timeless reality. Patterns that appear when you have large numbers of quantum degrees of freedom interacting in the right way. Patterns that observers embedded in those interactions experience as the flow of time. Time is not an illusion. It is an emergence. It is as real as temperature and as non-fundamental. The third position is that time is observer-generated. This is the most radical of the three, and in some ways the most consistent with the thermodynamic arguments we discussed earlier. On this view, what we call time is not merely emergent from the physics, but specifically generated by observers. by thermodynamic information processing systems that create records, store memories, form expectations, and in doing so impose a temporal structure on their experience of a universe that, at the foundational level, contains none. Time is something observers do to the world, not something the world does to observers. The river of time is real, but you are making the river. It exists in the relationship between observer and universe, not in the universe alone. No experiment has chosen among these three positions. No theoretical argument has been found compelling enough to achieve consensus. The question remains open, genuinely, rigorously, empirically, open in a way that is rare for questions this fundamental and this old. And it has been open in increasingly precise form since a specific morning in Princeton in March of 1949, getting sharper and more insistent with each passing decade rather than softer and more resolved. You have been walking through time your entire life, or through something so indistinguishable from time that the difference has never once, in the ordinary course of living, seemed to matter. You have memories. You have expectations. You experience the present moment as a moving edge, bounded and irreversible, separating a fixed past you can remember from an open future you can only anticipate. This experience is